Okay, so this is the first lecture during this time. So I hope that you enjoy. Anyway, we need to work together and try to finish the course. So I think we stop at 36. So today we will study 13.7 section. That's about tangent planes and normal lines. Okay. So do you see? Can you read it normally? Okay, I didn't hear anything. Anyway, yeah, we talk about tangent plane and normal lines. Okay, so let me tell you the motivation. We talk from time to time about partial derivatives, right? If you have some function z equal to f of x and y, we talk about partial derivative zx, zy, right? Means in x direction and in y direction, and we also talk about directional derivatives. And we mentioned several times, what happened if you have directional derivative zx and zy, both of them are zero, right? So if both of them are zero, so basically, tangent line to the curve in direction of x and tangent line to the curve in direction of y should be horizontal. So in this situation, they will form a tangent plane, which is parallel to the XOZ plane, ascends to the XOZ plane. So in that situation, that point would be the highest point locally, or maybe the lowest point locally. So that's why we are interested in partial derivatives, and then to find our critical points and to solve our optimization problems. Okay. But today, yeah, let's talk about tangent plane and normal line. Then you have some surface like this, and you want to find tangent plane. Of course, you need the normal line, right, to that plane, normal line, because we know from the very first chapter that in order to determine a plane, we need one point and the normal vector. You remember that? So one point normal vector that looks like, so if you have point A0, which is x0, y0, and z0, and you have some normal vector n, which is n1, n2, and 3. So you may define the plane passing through A0 and having n as a normal vector. And the equation looks like n1 x minus x0 plus n2 y minus y0 plus n3 z minus z0 equal to 0, right? Or if we want to write that in the dot product form, so we would have the following one: n times dot product ax equal to 0, where ax is what? Is this one, the first coordinate of ax, the second coordinate of ax, and the third coordinate of ax. So that is just ax and then n, that equal to 0. Because any x, whatever x in here, you have a vector ax will be perpendicular to n. So that's why dot product is equal to 0. Okay, so that is about tangent plane. So we need a normal vector to the surface. So if you want to write tangent plane, you need the normal vector to this surface at the given point. Okay, that is the motivation. All right, so secondly, let's look at this. So we need this equation, right? We need this equation. But our function is just function of two variables. So how to look at this function, okay? So where's that? Interesting. Okay, this thing here. So how to look at this equation? When we study level curves or level surface, so when we need to find level curves or level surface, we just put z equal to some number, right? But now I would transfer z, transfer z to the north side, and I get the following one. I just denote by f capital, f x and y and z equal to f x y minus z. And of course, because of this identity, this function is identically equal to 0. Identically equal to 0. Make sense? Okay, but you know, in this situation, it turns out that this guy, the surface, our surface, z equal to f of x and y, is just a level curve. Not a level curve, a level surface for the whole function in here. Make sense? Corresponding to z equal to 0. So our problem, you know, becomes just to find, to describe the normal vector to this function, right? To this function, you know, to this level curve, level surface for the 0. Make sense? And so, you know, for that we need, you know, we need to find partial derivative of this function. Find partial derivative of this function with respect to the x, with respect to the y, with respect to the z, and then we determine the normal vector. And then after that step, we will use this to write the equation of tangent plane. Okay, that's the whole idea, you know, how to find tangent plane to surface at a given point. Okay, now let me work out one problem and then you see how that works. Okay. So I will erase this. I want to keep this because we will need this function in the future. We need gradient of that function. So let's say we have an equation of equation of tangent plane. Okay. To tangent plane to z squared equal to 2x squared plus 2y squared plus 12. Or let's say, yeah, let's write minus equal to 12. Okay, so this is your, of course, you can solve this equation, right, to get z. That's fine. But now we will write in this form. We'll write in this form, okay? So we have the following equation. Here's my solution. I write f of x and y and z. You can write, you know, fxy minus z or z minus fxy. You know, this is okay. The only difference is, you know, with the size. So I write in this form z square minus 2x square minus 2, I think 2y squared here, minus 12. So that is our function. So in that case, they just write x minus, you know, z minus f of x and y. Agree? And then they have to find, you know, gradient of this function. That's the first step. The second step, find gradient of f, x, y, and z. So the gradient of f, x, y, and z looks like here should be partial derivative of this is negative 2x, partial derivative of this is negative 2y, partial derivative of this guy is just, you know, 2z. Okay, I think I didn't give you the point. So let's say to this guy at the point P equal to 191 and 4. Right? So once we have coordinate of this point, you can plug in, right, to find the gradient vector. And then the last step is just, you know, just write out, apply this to write. The last step is the equation of the plane. The equation of the plane is just equal to gradient f dot product with, you know, I can write this is px equal to 0. Okay, so now in order to find this vector, you just plug x equal to 1, y equal to 91, and z equal to 4 into this gradient, right, to find the gradient. So if I plug everything into that, I get the following vector. X equal to 1, I get negative 2, y equal to 91, I get 2, z equal to 4, I get 8 in here, right? A in here. And then what is Px? Px is x minus 1, y plus 1, and then z minus 4, and this equal to 0. And then you just multiply them together, you get the equation. You get the equation of the tangent plane. Okay, let me explain you why do we have this equation? Why we need gradient of the f? Okay, why we have gradient of the f? Look at this, please. When we study, I think somewhere in the previous sections we study level curves, and when we study gradient, right? When we study gradient, we had one theorem. It says that the gradient of that function is perpendicular to the surface, to a level surface or level curves. Do you remember that? So when we study a problem like heating seeker, which is particle onward continuously moves in the direction of maximum increase of the heat. Do you remember that? And then each time, that's the first problem. We solve two problems. The first problem, just find the direction of the maximum increase, which is gradient. The second problem is describe the curve of the particle. If particle is continuously moving along the direction of maximum increase in heat. And then after that problem, we say, yeah, we figured out, yes, each time the gradient of that function is, perpendicular to the level curve. And that is true for the case of function of three variables. The gradient function is perpendicular to the level surface. And look at this. We figured out that the surface of this function is just a level surface of this function. You see that? The surface of this is nothing but the level surface of this for the value 0. So that's why when you want to find the gradient of this function, so because thanks to that the gradient of this function is perpendicular to the level surface. So that means from here I get gradient of f is perpendicular to the level surface, which is the surface, right? Which is our surface from the original. So that's why that is the gradient vector of this function will be the normal vector for this surface. From there, you see, yeah, in order to find the tangent plane, I just take the normal vector dot product with with the one I have right there with the px. And of course that is 0. So that's why you have this relation and you use this relation to write the equation of the tangent plane. Make sense? Okay, to finish this problem, let me just write out the equation and then we move to the next example. So, here we have -2, 2, 8, but we have 0 in here. I can simplify 2. So basically, I just need in here, I don't know if you can see that or not, but I just need -1 in here and just 1 in here and then just 4 in here. And then I multiply them together, I get -x minus 1 plus y plus 1 and then plus 4 times z minus 4 equal to 0. So this is my equation of the tangent plane. If you want, you can simplify that. You get -x plus y plus 4z. And then what else? Negative with -1 is 1. 1 plus 1 is 2. 2 minus 16 is -14 equal to 0. So you see, it's not that bad, right? It's not that bad. Okay, so I mentioned again, right? If you have any question, just stop me and then ask me as usual. Okay? If you don't stop me, you don't ask me. So I just go ahead to finish example, so we can finish online lecture sooner. Okay, earlier a little bit. But I hope that this example is clear enough. The most important is if you understand this equation and why do we have that, so we are done. So let me explain a little bit, just one more time, okay? So we want to find a tangent plane to the surface at some point. So we don't do that directly. We will write this equation as f of x, y, z equal to f x, y minus z, or z minus f x and y. And since we have this identity, the whole function is equal to 0. So what happened? That means the surface of this, our surface is just a level surface of this function for the 0. And we know if we have level surface, so the gradient of this function is perpendicular to the surface, to the level surface. So that means, you know, gradient of this function is the normal vector of the surface, of our original surface. So that means we just need to find normal vector, just, you know, gradient of this function, right? Just take partial derivative with respect to the x, with respect to the y, with respect to the z, and then, you know, since we should have one point over there, and then if we have that point, just write the equation. All right. Now let's move to the second example. Okay. Find equation of the tangent plane to the paraboloid. Z equal to 1 minus 1/10 x squared plus 4y squared at 1, 1, and 1/2. So, you know, as we have seen in the previous example, we only need to find gradient of the function, right? And first, we need to generate the function f capital, right? So, what is f capital X, Y, and Z? In this case, you can write Z minus, or, you know, you bring Z to north side. No difference. The only difference, you know, is in sign here, but the product is already 0. So with minus or with plus, it's no change in that. So I have Z, I can write Z plus 10 x squared plus 4y squared and then minus 1, okay? So that is our function. Now, just bring all terms into another side, so I get Z minus with negative will be plus, 1 will be negative 1, okay? Now just find, you know, gradient of f. So you can do that like partial derivative of this guy with respect to the x. This is 0, this is x over 5, because in here we have 2x, 2 with 10 will be simplified, right? I get 5 here. And then I differentiate with respect to the y, I get 8y over 10. So 8 over 10 would be 4 over 5. All right, 4y over 5. And then partial derivative with respect to the z is just 1. Is it? And then you plug 0.1, 1, 1/2 into this. So I can write it, I can find that, you know, vector right away. So we don't have to wait. Let me see. So I can write it. When x equal to 1, I have 1/5. Okay. Y equal to 1, I have 4/5. And then when z equal to 1/2, it's just 1, right? You know, 1/2 does not affect on this because you have 1 in here. And then you just write out the equation. Gradient f times, let's say, if this is a, so I can write ax equal to 0. And you know, we don't have to write that equation again. So now we will just write it in short. I write in the following way. You know, look at this. I take here we have gradient, right? So the first coefficient is 1/5. I write it right away. X minus 1 plus 4/5. Y minus 1 plus 1. Z minus 1/2. And all this equal to 0. So you see, we are done, right? You don't have to write like coordinate of this, multiply with this, just write that directly, okay? Just save a little time. So that is about, you know, the problem, how to find a tangent plane to a surface. Okay. Let's do one more problem. And then I think with that we can finish today's lecture. Okay. So find an equation of the normal line to surface. Right. So the surface looks like x, y, z equal to 12. And the point is just 2, -2, and -3. Now look at this. What is the difference between these two problems? How do you think? What is the difference between them? Actually, there is a very minor difference. In this situation, they ask us to find tangent plane, right? But in order to find tangent plane, we need to find what? In order to find tangent plane, we need to find the normal vector. You see that? And once we have normal vector and one point, we can write a tangent plane. In this situation, they ask us to find normal line to the surface. You know, normal line, that is surface, and we just figured out the gradient is the normal vector to the surface, right? So basically, all we need is this, right? This is the same. I mean, the steps in here should be the same for that problem. The only difference is in here. So here, we need to write equation of the plane. But in here, we need to write equation of a straight line. And in this situation, gradient of the function will be the direction of this straight line. Make sense? All right. So in order to solve this, I need to write f of x and y and z equal to x, y, and z minus 12. Okay, minus 12. So I can differentiate this function. Okay, let's find gradient of this function. By the way, we have to do that correctly. Fz. Okay. Let me finish, right? And then we'll figure out is it correct or not. Because usually we start from where? From z equal to f of x and y. So do we need to write z equal to 12 over x and y or not, and then differentiate that? I don't think that we need that. I don't think we need that. Anyway, we can do this. So like we have this function is defined, you know, like this. So if we put this equal to 0, it's almost the same. So our surface look like this. Yeah, that would be good. So the gradient would be yz, xz, and then xy, right? That is the gradient vector. And I plug 2, -2, -3 into this. I will get the following one. X equal to y, -2, -3, so I get 6 in here. X with the z, I get -6. And then x with the y, I get -4, okay? So that is direction vector. We have direction vector, we have a point. So we can write the equation of that straight line. I hope you still remember. We have two forms, right? The first form is canonical form, and the second one is parameterized form. So let me write pole for you. If we write in canonical form, I will have the following one: x minus 2 over the first coordinate of this. But we don't have to use 6. We might simplify 2, right? So I can write just 3. And here I have y plus 2. Plus 2 because y minus 92, I have y plus 2. I have -3 in here. And then I get z. Here 93, so I get plus 3 over. I get 92. So that is the equation of the normal line to the surface at this point, you know, in the canonical form. Okay, we can write it in the parameterized form. In the parameterized form. So I will parameterize. We might write like x equal to the point, y equal to z equal to. So I just copy coordinates of the 2, -2, and -3 in here, right? That is the coordinates of the point. And then I just add this one with the t. So I get plus 3t, minus 3t, and then minus 2t. So that is parameterized form of the normal line to the surface. Okay. So I think I can stop the lecture in here. It seems to be short if we compare with the face-to-face class, but you know, for the face-to-face, since we have to interact with you, it takes more time. Okay. So please let me know if you have any question about this. Unmute your microphone and ask me a question if you have, please. Is everything good?
I think so.
Okay. So if you don't have any question, we can stop the lecture right here. And tomorrow we'll keep this time, okay? Just meet with you online during the class time. Okay? And I will post a video of this lecture to my YouTube channel and send out a link to you in case if you need to review it. All right?
Better.
All right. Thank you. And please be safe. See you tomorrow.